Okay, can you see the slides? All right. Last week we stopped at ohmic contact. Okay, we've discussed about Schottky. We've discussed about the mechanism inside Schottky, and then we've discussed also ohmic contact. Right. So let me just recap on what we left off last week. So recap that Schottky is a resistive junction. Okay, so it only allows one direction of the current flow. So it takes shape of a typical diode IV curve. Okay, exponential in the positive region, the fault bias region, and then it's just flat. It's just a flat region with a small leakage in the negative region. For ohmic contact, it's a low resistance junction, so it allows the current to flow in both directions, positive and negative. Okay, so the shape of the ohmic IV curve is just a straight line with a positive gradient. Okay, so we have discussed about the flow of the electrons in metal to semiconductor or metal or semiconductor to metal according to the level of the Fermi level or Fermi energy, EF. Okay, so now you know that if the EF of the system, so the system here, I mean metal semiconductor system, before they join together as an interface, if your EF of your metal is higher than the semiconductor side, then that means electrons are going to flow from the material with higher EF to lower EF. Okay, so the same is also true for semiconductor. If your semiconductor has an EF higher than the EF of the metal, then we're gonna get the opposite flow of the electrons. Okay, so to be able to know the EF, you have to first draw the band diagram before the metal semiconductor are joined together. Okay, before they reach the thermal equilibrium condition. So to be able to do the drawing, you firstly have to know whether the material is N-type or P-type, the semiconductor is of N-type or P-type, and then you also have to know the work function of the metal and the semiconductor. Okay, just like what we saw last time in this table. So since we are now talking about ohmic contact or ohmic junction formation between metal and semiconductor, so if you're talking about N-type semiconductor, then we know that the EF of the semiconductor is close to the conduction band or the EC. And to be able to have an ohmic contact for N-type semiconductor, the work function of the metal has to be less than the work function of the semiconductor, which brings us to this page. So phi for the M is less than phi S, therefore phi M is less than phi S. You can see the magnitude here, right? The distance, which is measured from the Fermi level of both materials to the vacuum level, right? The vacuum level, E0, vac level. So in this case, the semiconductor is N-type. Work function of the metal is less than work function of the semiconductor in order to form an ohmic contact. So what happens next? To achieve thermal equilibrium, upon the combination of the metal and semiconductor, the electrons have to flow from the metal into the lower energy states in the semiconductor, because we already can tell the EF of the metal is higher than the EF of the semiconductor. So therefore, electrons are flowing from the metal into the semiconductor in order to establish thermal equilibrium. Okay. Excess electrons in the N-type semiconductor exist essentially as a space charge density, right? So if a positive voltage, so if a positive voltage is applied to the metal, okay, if a positive voltage is applied to the metal, okay, this is the left-hand side is the metal, the right-hand side is the semiconductor. So therefore, here is also true, metals on the left, semiconductor on the right. So now you've got the thermal equilibrium already. So now we're trying to do biasing. Remember, you have to do the biasing upon TE is established. Okay, thermal equilibrium has to be established first. Then only you apply the biasing, either forward bias or reverse bias, for example. So in this case, a positive voltage is applied to the metal. Maksudnya is more the voltage on the metal is more positive relative to the semiconductor. Maksudnya metal is positive relative to the semiconductor, and the semiconductor is n-type. Maksudnya, what sort of bias are we applying here? Which bias are we applying here? Metal is connected to positive, and negative. A semiconductor is connected to negative, and the semiconductor is n-type. So what sort of bias are we applying now? Anyone? Bias apa tu? Anybody? Remember last time when we talked about PN junction? Okay, forward, right? So forward sebab negative, in this case, the semiconductor is connected to the negative, okay? So hence, there is no barrier to electrons flowing from semiconductor into the metal, okay? So you are biasing the forward, you're biasing the junction in forward bias. So if a positive voltage is applied to the semiconductor, on the other hand, kita terbalikkan dia pula. Now we're looking at ohmic contact, and remember that in ohmic contact, the current can flow in both directions. Okay, it's not the same as the forward and reverse bias in a typical PN junction made of semiconductor materials. So in the second case, if you apply a positive voltage to the semiconductor, in the second case, tadi first case ke atas. So now the second case, applying forward semiconductor, forward bias, relative to the metal. Relative is always relative. If one is forward, then the other one is, sorry, if one is positive, then the other one is reference lah, reference. So effective barrier height for electrons flowing from metal into semiconductor will be approximately phi Bn equals phi n. Phi Bn and phi n are given in this diagram, okay, which is not that big, which is fairly small for a moderately to heavily doped semiconductor. So this barrier height is typically modest. Okay, modest maksudnya small, quite small. It's not that big. So it won't prevent the flow of carriers. Okay, moderately, so fairly small for moderately doped semiconductor to heavily doped semiconductor. So for this bias condition, for the second case, electrons can flow easily from the metal into semiconductor. Dia terbalik ya. Tadi case number one. So let's revisit case number one. Electrons are flowing from semiconductor into the metal. Semiconductor into the metal. Electron flowing. Case number two, electron can flow easily from the metal into semiconductor. So we're going to have bidirectional current flow, both directions, because electrons are now flowing to the other side, on the opposite side, okay? So to relate this to the IV curve, you're going to have this IV curve for the ohmic contact. So we are allowing the currents or the carriers to flow in both directions with the right biasing condition, okay? So case number one, you're going to get electrons flowing from a semiconductor into the metal. Then for the case number two, we're going to have the opposite direction of the electron flow. So this is how it looks like when you want to zoom into the carrier flow. So look at the figure on the left, 9.12a. Energy band diagram. When a positive voltage is applied to the metal, okay, positive is applied to the metal. Let's just do the very same connection macam kita buat tadi. Okay, so positive voltage is applied to the metal, negative to the semiconductor. Let's do the same thing. So if you're confused, then always try to draw this, okay, so that you know the biasing condition more clearly. Applied to the metal, okay, with respect. So with respect means the reference, so maksudnya dia lebih negatif lah. On semiconductor side is more negative. So electrons flow downhill from semiconductor to the metal. So this is what we get. Electrons are flowing from semiconductor to the metal, just like we saw in the first case. Electrons are flowing from semiconductor into the metal. So for the case number 2, a positive voltage is applied to the semiconductor, just like in our previous page. On our previous page, positive is applied on the semiconductor with respect to the metal. Okay, label clearly, metal, semiconductor, metal, semiconductor. So electrons can flow easily in the opposite direction over the barrier from the metal into the semiconductor, even though the barrier is there, right? The phi Bn, phi n, right? Phi Bn on the metal side, and phi n on the semiconductor side, of equal magnitude, but both of them are small or fairly small, modest. Means it's not that difficult for the electrons to cross, right? To jump over, flow over the barrier here, over the barrier. So this junction then is an ohmic contact. So since we have bidirectional flow of the carriers, so we will end up with the straight line IV curve, right? The straight line IV curve for an ohmic contact. So in ohmic contact, we also discussed about a tunneling barrier. Okay, we can also have a tunneling barrier. So on top of the current ohmic contact formation, the sub of the ohmic contact is called a tunneling barrier. Still ohmic, but tunneling in this case. So why do we get tunneling? How do we get tunneling? So let's look at the explanation first while looking at the schematic on the left. So the space charge with inner rectifying metal semiconductor contact is inversely proportional. Inner rectifying, okay, dalam junction rectifying is a Schottky, right? So inversely proportional, okay, the width, if you like, the depletion region is inversely proportional to the doping level, right? So the square root of the semiconductor doping, Na or Nd, doesn't matter. So the width of the depletion region decreases as the doping concentration increases, because they are of reciprocal in nature. Okay, so higher semiconductor doping will lead to smaller depletion region. So if the doping keeps increasing, if the doping is high enough and the depletion width is getting smaller and smaller and smaller, so that will increase the probability of tunneling through the barrier. Okay, so bila you punya barrier tu is getting smaller and smaller, so it's a lot easier for the carriers to cross because the barrier is not great enough. Okay, so if you look at this, figure 9.14 shows a junction in which a metal is in contact with a heavily doped. Okay, tengok ni heavily doped. The key word here is heavily doped N-type. Okay, epilayer ni we're going to learn later on. Epilayer ni is a very thin layer formed on a substrate. A very thin layer, epitaxial in nature, means like when you do the deposition, when you deposit the layer on top of the substrate, it's going to be deposited layer by layer. It's not like coming all the atoms or molecules coming together at the same time. So they're going to be deposited one by one. Satu layer. It's just like, pernah makan kek lapis kan? Have you seen kek lapis? Pernah tengok kan kek lapis? Kek lapis kan? So, kek lapis ataupun kuih yang apa tu, yang warna pink putih tu kan? So kuih lapis lah kan? We call that kuih lapis, right? So you prepare layer by layer. So just like the epi layer lah, just like the epi layer. So it's not like you got to learn this one a lot more when we learn about 487 later on for applied lah. When you learn about film deposition technique, how do you do deposition? By sputtering, by evaporation, thermal evaporation, electron beam, and MBE, and spin coating, all those stuff. So different deposition methods have different nature. Okay, a certain deposition method, for example, they sort of deposit molecules many and many together at the same time. But if you talk about epitaxial deposition process, it involves depositing layer by layer of the intended materials on the substrate. Therefore, we're going to have a better control of the uniformity, better control of the crystalline structure, and other properties of the material in the epitaxial layer deposition. Okay, so this one is just a brief. So to be able to have an ohmic contact which allows tunneling to happen, you need to dope your n-type in this case heavily, right? So let's recap on what we've learned about band diagram. Okay, so when we draw band diagram in an n-type material, the EF is close to the EC, right? So EF is close to the EC kan? So this is like your n-type. So this is your n-type semiconductor. You can see that the EF is close to EC. Then you also have in the central part, we also have semiconductor still. But in this case, the n-type is not n-type, it's called n+. N+ means n-type that is heavily doped. You may also encounter notation like n+, n++, right? And this plus and plus signifies the range of the doping level, okay? Range of the doping level. So typically, if you talk about n+, then we're talking about 1018, 1019, right? So if you're talking about plus, it's going to be high 19 or 20 per centimeter cube, the doping level. So both this on the right onwards is the n-type semiconductor, and this one on the left is the metal. Okay, you can tell, right? You can tell. How do you tell it's a metal now? How do you tell the left one is metal? If there's no label, then can you tell it's a metal? How do you tell from the band diagram that metal is on the left? Anyone? How do you tell that metal is on the left and semiconductor is on the right? Semiconductor is quite clear there. How do you tell it's metal? Okay, jangan tengok ni, you can comment here. EC and EV there. EC and EV, what do you mean? Do we have EC and EV for metal, Faris? Do you see EC and EV for metal? Faris? Do you see on the left, do you see EC and EV? No, right? You only see, so what you only see on the left? EF, right? So when you see only EF, so that means it's a metal. On the other hand, if you look at the right-hand side, then you can find EC, EF, EV, right? The typical schematic band diagram of a semiconductor on the right. So kalau you nampak just EF, then that means it's a metal on the left. So metal is on the left, but the center to the right is all semiconductor. So how do you tell it's N plus? Can you tell it's N plus from the band diagram? How do you tell? Any idea? How do you tell it's N plus? Anyone? Ada idea tak? Any difference between N and N plus in terms of the band diagram? What do you get there in the central region? Ah, the dip, right? The dip or the bending. The bending between the bending in the EC, the bending in the EV, right? The EC and EV ada bending sikit. The dip or the bending, if you like. But the EF, does it bend? Do we have a bend in EF? No, right? So there's no band in EF. So EC and EV, in this case, is more specifically EC, sebab we're talking about N-type material. So if you see in N plus, look at the EC, the distance between EC and EF. EF is closer to EC or not in comparison to N saja, N-type. Closer, right? So we learned last time about the definition of EF, right? So lagi tinggi dia punya EF, lagi tinggi dia punya doping level kan? We talk about that, right? Remember when we talk about intrinsic where the EF equals to EI, right? It stays right in the middle of the band gap Eg/2. But as you increase the N-type doping level, so the EF is going to increase, closer and closer to EC, isn't it? So for the N-type, yes, you can have that distance just to set the reference, if you like. But if you increase the doping for the N to be N plus, close to the surface there, so that means your EF in the band diagram should be closer to your EC. Okay, EF is closer to the EC. You can tell by the distance there and by the distance here of comparison. Right, to be able to accommodate the change in the EF, so the change in the doping level, so the EC has to bend accordingly to be nearer to EF, because EF is just a single line, single chemical potential at thermal equilibrium. So the EC has to bend accordingly dekat border between N and N plus in order to accommodate the closer nature of the EF to EC in N plus, right? And in this case, if your N plus is high enough, and I think in terms of the doping and also the thickness, doping has to be high enough, but the thickness has to be low enough, just right, not so thick. We will have tunneling of the carriers. Okay, we will have tunneling of the carriers across metal semiconductor junction. Okay, kita tengok lagi ya. So if you want to translate this into a physical drawing, okay, kalau kita nak lukis physical drawing, so this is just a band diagram. So let's just draw a wafer, for example, silicon wafer, just to make it clear with the physical life or physical size. Okay, so say this is the metal that we are talking about. Okay, katakan ni you punya metals, I label as M on top of the silicon. So this, the wafer and the silicon here is like the band diagram, but you flip 90 degrees clockwise. You flip 90 degrees clockwise. Then you're going to get metal to semiconductor interface, just to compare so that you are clear. Takut you lost. So metal is on top of semiconductor. So this is N-type silicon, N-type silicon, and silicon. So the whole wafer is N-type silicon. But on the surface of the silicon wafer, we have a very thin layer, epitaxial layer, heavily doped with N+. Say this one is N+ silicon. Okay. So you may have this N silicon, the whole wafer is probably, say, 200 micron. But your N+ is only like 5 nano, for example, 5 nanometer. of N plus in comparison to 200 microns. So big the difference, right? More than 1,000, 3 orders of magnitude logarithmically, nanometer to micron, and it's only like 5 nano in comparison to 200 micron of the whole wafer thickness. So imagine how thin is the epitaxial layer N plus dope in order to enable the tunneling process. I think let me find some good tunneling video for you to share, okay, on e-learn later on. I'll let you know. So this is just a summary of what you've learned before this about the Schottky contact or rectifying contact, which takes that form. So now you've learned about the mechanism of the flow of the carriers in the Schottky contact. When you meet certain conditions, so especially when you refer to the work function of the metal versus semiconductor and look at whether the semiconductor is N-type or P-type. Okay, and the same we've learned as well for the ohmic contact formation and also the possibility of getting tunneling across the metal semiconductor junction. Okay, so that's the theoretical part of the metal semiconductor junction. In real life, when you run experiments, so the metal semiconductor junctions rarely behave as predicted by this simple model. So the key word here is simple model. So this is what you can use to design or to adhere to as the theory as a fundamental for your experiments. But say if you want to get ohmic contact in real experiments, it's not as simple as this in this condition. Okay, normally in real cases, even though you're designing your junction p-type work function whatever to get ohmic, you'll probably end up with Schottky still. If that means if you measure your IV, you'll probably end up with one directional behavior of the carriers. You may end up with this even though you've designed your junction to be ohmic in nature. Why? So there are a few reasons for that. Some reasons are as below, right? Surface states. You may have some surface states between your semiconductor, your silicon, to your metal. So it's not a clean interface of pure metal and pure silicon. There are something in between. You may have some surface states in between, right between the interface of metal and semiconductor. There's a very thin layer of something else that disrupts the theoretical behavior of the ohmic junction. Okay, so there could be impurities at the surface as well. You may have some defects or something unwanted on the surface. You may have some interfacial reaction between the metal and your semiconductor at the surface, especially if you are processing the junction under high temperature conditions, for example. Then that may induce some unwanted reactions on the surface. So as a result, instead of having ohmic contact as designed or as predicted by the theory, you may end up as a Schottky contact. But this can be repaired or can be prevented if, for example, if you're talking about impurities at the surface. So that means before you evaporate your contact, before you deposit your contact on the semiconductor, you have to make sure that the surface is really, really clean. There is no interface. There's no impurities on the surface at all. So that means the surface has to be super clean before you deposit the metal on the semiconductor in order to ensure ohmic contact formation. If you're not careful enough, so if you run your FYP and you want to get ohmic contact, ohmic metal semiconductor junction, tapi you don't do the cleaning, or there's a native oxide in between. For example, you didn't do HF dip, hydrofluoric acid dipping, or you didn't really clean the contaminants on the silicon surface, tapi you choose evaporate metal contact right on the semiconductor, then you'll probably end up with rectifying contact or Schottky contact instead of ohmic contact. So those are the possibilities, and it's normal to have that kind of observation. So is that a way to ensure ohmic contact? Yes, of course, you can do the cleaning. You can make sure the surface is super clean. You can also do thermal annealing if you like. Anyone working on annealing in your FYP? Ada orang buat? Insert the sample in a furnace and heat it up to high temperature, probably. Anyone working on annealing, say 500 degrees C in nitrogen ambient, or you can do in oxygen ambient. It can also be in some other gas conditions, but at high temperature. Yeah, not you, right? So, yeah, well, there may be some of you working on annealing. So that can help to induce, if let's say you're supposed to have ohmic, but you don't have ohmic, but instead you have Schottky, what you can do, the outside team, okay. So what you can do is you can input a sample or put a sample in a furnace and ram the temperature at high temperature, at certain temperature, in certain ambient condition, then you may end up with ohmic contact eventually, right? But you have to look at the right parameters, temperature, time, ambient, surface condition in order to ensure ohmic contact formation. So this is just another Venn diagram, similar to what we've discussed on the previous page. So we can see N plus, check out here, N plus and metal on the left, okay? So you can see the EF is much closer to EC. This one is not as close to EC, to illustrate the effect of tunneling effect, okay? The bending, you can see when you get the bending of EC, the EV also bends accordingly. Okay, done. Metal semiconductor junction is done. Is it okay so far? Okay, are you clear now of ohmic contact, Schottky contact, mechanism, what prevents ohmic contact formation, what are the conditions for the tunneling? Okay, so far? Yeah, so far so good? Right, let's continue with semiconductor heterojunction for, say, 15-20 minutes. Sort of, okay. Sort of means good. Right, can you see the slide now for semiconductor heterojunction?
Yes.
All right, it's good. So this is semiconductor heterojunction. So like usual, you should be able to answer these questions. Challenge what you've learned. Okay, let's go through briefly. For a semiconductor, why do we need metal contacts on semiconductor? Why contacts in the first place? Anyone? Come on, let's spend only 5 minutes or below. Yes, just to make sure that you're doing okay. Right, nak bagi electron flow. Okay, nak bagi electron flow. Increase conductivity of the semiconductor, you mean? Azik? Well, it's not direct. Usually we use the metal contacts in order to extract the carriers or to induce the carriers into the semiconductor. Okay, so but you may be correct. It can also increase the conductivity of the semiconductor if you do something at the interface of the metal and semiconductor. So that requires elaboration. For example, so if you want to increase conductivity in the semiconductor by using metal, then you have to anneal the junction of the metal semiconductor at a high temperature in order to induce diffusion of the metals into the semiconductor in order to form a better contact. In that case, you will increase the conductivity of the semiconductor. But if you leave your explanation only to increase conductivity, it doesn't make sense just yet, right? So it requires further elaboration, okay? So what does it mean by rectifying and non-rectifying contacts? Apa maksudnya? Rectifying and non-rectifying contacts. Okay, one flow and both flow. Rectifying allow current in one direction, while non-rectifying, yeah, okay. So rectifying allows current in one direction, and non-rectifying allows current in two directions, okay. So rectifying just like the diode, the IV curve, kan? So it's exponential in nature in the forward bias, and there's no current flow in the reverse bias, right? It's good. So on the other hand, if you talk about the non-rectifying, we're talking about the ohmic contact, right? Allows bidirectional current flow. So draw a band diagram. We cannot draw this now. Okay, make sure you know how to draw this. Okay, kalau you tak practice, then the chances are you don't know how to draw. Okay, try to practice drawing the band diagram for the junction under thermal equilibrium, forward bias, reverse bias, and label all the important parameters at the same time. Right, last one, explain about tunneling barrier. What is a tunneling barrier? Anyone? Alisha boleh jawab. Okay, come on, Alisha. You are appointed to answer. Anyone? Tunneling barrier? So if you're asked to explain, then just go back to the notes just now, right? So those are the things that you have to explain. Band diagram, label, what's happening, what is required of a tunneling, why do you want to have tunneling? Okay, space charge width and rectifying, right? Depletion width and just now the doping level, epitaxial layer formation, N plus, EF position, and all those stuff, right? Okay, N plus, thin layer, heavy doping, right? Thin layer in order to allow tunneling to happen. Done. Let's move on. Heterojunction. So when two different materials with different band gaps, so the key word here is different band gaps, two different materials, different band gaps are combined, we're going to have a heterojunction. Remember last time when we talked about a p-n junction, so we used to talk about crystalline silicon with a band gap of 1.12, right? Across the whole wafer thickness. So, and then we started talking about p-type here and then n-type there, but the whole material is still the crystalline silicon, the same crystalline silicon with the same band gap across the material. So then we were talking about homojunction because both sides of the p and n have the same band gap. So in this case, when we're talking about heterojunction, we're talking about two different materials or same material, well, not the same exactly, with two different band gaps. For example, if you're combining crystalline silicon with amorphous silicon, okay, so you're combining at the interface, say in this case, you're combining crystalline silicon with amorphous silicon. So what's the band gap of amorphous silicon? Crystalline silicon here, 1.12. What's the band gap of amorphous silicon? You can go search now. Berapa band gap dah? 1. Apa ni? Amorphous silicon? Someone please search and tell me. What's the band gap of amorphous silicon? Okay, 1.75, 1.8, lebih kurang tu lah. Usually you'll normally find 1.7, 1.8, right? So say about 1.8. So now we are combining 1.1 with 1.8, right? 1.8 and 1.12. So therefore, it is a heterojunction. Okay, just like what we see in this device. So this is a device. Actually, is a solar cell. For example, is a solar cell mass manufactured by Panasonic. Panasonic Energy. Do we have this Panasonic in Malaysia? Okay, we have this Panasonic in Malaysia. Ada orang Kulim kat sini? Ada orang Kulim? Go orang Kulim kan? You pernah pergi Kulim High-Tech? Go. Pernah tengok Kulim High-Tech? Park. Pernah kan? So have you seen Panasonic? Pernah nampak tak? Okay, Panasonic is near Celestica, near Silterra, right? Belah sana tu. Belakang sikit. So Panasonic. Okay, well, yeah, they used to run the business in Malaysia, in Kulim High-Tech to be more specific, tapi dia baru withdraw from solar cell industry. So dia akan, I think they're going to close the business in August, if I'm not mistaken. So kawan-kawan saya yang kat sana will be jobless in the 2 months time, for example. So they're gonna be out. So they were dealing with a China company called Sun Everywhere. Kalau you pernah dengar, you can search this. Sun Everywhere is a company from China. Buat solar juga. Dia nak start business ni dekat Sun Everywhere, but I think the deal is not happening. So the business is going to be closed. So Panasonic used to be one of the best solar cell manufacturer in terms of the efficiency of the device. So the device that we're talking about is here. You're looking at the device now, where you can see here the N-type crystalline silicon is used as the central material, but the crystalline silicon is sandwiched. Dia diapit oleh amorphous silicon on top and at the bottom as well. So you tengok dekat atas ni, the top region is intrinsic amorphous silicon, means undoped, followed by N-type amorphous silicon, followed by a TCO. A TCO, kita dah belajar kan? Degenerate semiconductor, they use ITO here to be the transparent contact, to produce transparent contact. So they also have intrinsic silicon at the back, undoped, a very thin one, I think about 10 to 20 nanometer, and then followed by a TCO contact at the back as well. So remember, I think in the last lecture, we discussed about non-metal contacts, right? So you mentioned about semi-metals and degenerate semiconductors. So this is the real device that we are looking now, ITO contacts. Even though you can argue here that they also have metal contacts on top, but some of the conduction process, extraction of the carriers is done in the ITO layer here, in the ITO. Yang purple ni. So the electron extraction and the hole extraction is done in this layer. Laterally maksudnya along the thickness of the TCO. Within the channel tu lah, dalam channel tu, dalam thickness tu. So it's called lateral conduction. Okay, even though they still have front metal contact and rear metal contact in order to improve the carrier extraction possibility, or the carrier collection we discussed last time. Remember the EQE, quantum efficiency and stuff. So this is a real life example of a heterojunction device. Okay, you will search on Panasonic later on, cuba faham dia punya device. So we are talking about different band gaps. Energy band will have a discontinuity at the junction interface. So whenever you combine a small junction, a low band gap with a high band gap, low band gap, low and high band gap. Yang low you akan ada small ECEV punya distance. The big one you're gonna have big ECEV distance. So when you have a small, a low, and the big one, remember the band gap is essentially EC to EV, right? So you're gonna have a junction like this, small to big and big to small, either way, right? So this result in a discontinuity at the junction, right? Sebab dia tak continuous lah, sebab dia punya size tak sama, EC and EV distance not same. So may have an abrupt junction in which the semiconductor changes abruptly from a narrow band gap to a wide band gap, narrow to a wide or small to big. Okay, say you're going from 1.1 to 1.8. So it is the same example. So heterojunction, you have to pay attention to lattice constant of the material. Of the two materials must be well matched. Okay. So you've learned a little bit of the lattice constant in solid state physics, right? The A, B, C, unit cell, and all the stuff. Apa jangan? Lattice constant? All right, good. Have you learned on how to calculate lattice mismatch in 307 solid state? Pernah belajar tak how to calculate lattice mismatch or lattice match? Did you learn last time in solid state physics? If you combine two different materials, then you're going to have some mismatch due to the different lattice constant. Ada belajar? Belum? Belum ni, right? So, but you learn about lattice constant, but this is applying the lattice constant to a real device. Sebelum kita belajar dalam 307, lattice constant material ni is this, and this one is this. But now you're combining to see what's going on the real device. Okay, so if you're combining narrow band gap and the wide band gap, the two different materials should have a lattice matching. Maksudnya lattice material satu and material 2 kena match. If the lattice matching is not happening, or we call it lattice mismatch, then at the interface we're going to end up with defects. Maksudnya dia duduk tak betul lah. Macam you see, for example, if you normally I demonstrate this in our lecture, but we don't have the lecture hall to show. Macam you duduk atas kerusi, but you don't sit right in the front of the chair. Kerusi duduk tengah, tapi dia tak duduk kat tengah, duduk kat tepi kerusi tu. Atau duduk kat depan kerusi, duduk kat ujung kan. So you're not stable then. If you don't sit properly right in the center of the chair, then you will not be stable. Kalau orang tarik kerusi, then you lagi senang jatuh lah. Because you just sit at the tip of the chair, for example. Ataupun you duduk tepi. Ataupun you duduk dislocation, right? Dislocation. So you tak duduk properly. So the interface between you and the chair is actually a defect, a form of defect. So the same goes to the lattice matching situation, right? So the lattice matching is important because any lattice mismatch can introduce dislocations. So if you have a mismatch between material 1 and 2, narrow and wide band gap, you're going to have dislocations, and dislocations are defects. So the moment you have defects, you're going to induce unnecessary recombination. We learned last time about Shockley-Ritz-Hall, which are based on defects. Okay. So for example, if you have defects, defects are physical in nature, means you can see or you cannot see perhaps, but they are physical in nature. But these defects, if you want to translate these defects as an electronic representation, they will be representing themselves as interface states in the band gap. So see, this is your EC, this is your EV, then you're going to have trap states somewhere in the band gap, okay, due to the dislocation. So kita dah belajar hari tu on the Fermi energy and stuff. For example, if we're talking about germanium and gallium arsenide, if you're combining germanium is about 0.7 EV and gallium arsenide is about 0.4 EV, 1.4. So we are combining 0.7 and 1.4. Then the lattice constant match. So they are match, and the mismatch, if you do the calculation, is within 0.31%, the mismatch level, which is not big, right? It's just a small mismatch. Therefore, they are okay to build a heterojunction. On the other hand, gas and all-gas, gallium arsenide and aluminium gallium arsenide, we normally say this as gas and all-gas junction, have been investigated quite thoroughly, and the lattice constants resulting in a calculation of 0.14%, which is okay. So let's recap on this. Let me continue with another 2 pages. So lattice constant that you learned last time in 307, you can look at this range of materials with different lattice constant. Okay, aluminum arsenide, silicon, indium phosphide, magnesium oxide, silicon carbide with their own crystal structure. Okay, so let's look at this graph. So if you want to combine, for example, 2 different materials with 2 different band gaps, just now we talk about germanium and gallium arsenide. Germanium and gallium arsenide, 0.13%. So let's look at germanium and gallium arsenide. So germanium is here. So the band gap is about 0.7. On the y-axis is the band gap, and lattice constant on the x-axis. So you need these 2 parameters to decide the matching. So gallium arsenide is here. So the band gap is about 1.4 on the y, and the lattice constant is pretty close. Germanium is here. Gallium arsenide is here. Okay, so they are quite close together. So therefore, these will result in the small percentage given on the previous page, 0.13%. Okay, matching. So therefore, it's a good idea if you want to combine these 2 different materials as a heterojunction, because the lattice constant of both materials are pretty close to each other on the x-axis. Okay, you think on the x-axis, you can tell already. For example, if you want to combine cadmium telluride on indium arsenide, is it a good idea to combine this as heterojunction? Cadmium telluride and gallium arsenide. Okay, It's not a good idea, right? Because the lattice constant for cadmium telluride is like 6.4 something here, and on the other hand, the other guy, indium arsenide, is about 6.05 or so. So that will result in a bigger mismatch, okay? In a bigger mismatch. So the same goes to other materials as well. If you want to combine two different materials with different band gap on the y-axis to form a heterojunction, this lattice constant factor is a very important factor. Quality, the electronic quality, to be more precise, of the heterojunction. Lattice matching is very important. If not managed well, will lead to dislocation and states in the band gap, right? Just like what we drew just now, ECEV and states in the band gap due to the presence of dislocation. For example, if you're combining these two together, and you're going to end up with dislocation representing themselves as trap states, and this will suck your carriers from the system eventually. So this is some of the examples when you deposit epitaxial layer. Remember we talked about epitaxial layer formation last time. Deposition, a very thin one, layer by layer, so that they follow the crystal orientation of the underlying crystal or the substrate. So here, if you want to deposit the epi layer, you want the epi layer to take on the crystal structure of the substrate. Okay? You know, to follow exactly the crystal structure of the substrate. So that's why you do the deposition layer by layer, slowly, in order to make sure that the crystal growth is ensured, okay, the way we want it to be. So lattice match, this one is a bit strained and this one is constrained, unstrained. See the matching. Okay, done. So try to go back and try to see the equation, search the equation on how do we calculate lattice mismatch. And later on, tomorrow perhaps we can come to this and try to see if you want to pair aluminium antimony on silicon, then what do we get? How about others? Cadmium telluride on silicon, what do we get? Such a big lattice constant difference, right? So try to see that, and then we're going to move on to energy band diagrams of narrow and wide band gap, and how do they look like when they are in thermal equilibrium. And then this is the real device that I was talking about, the silicon heterojunction solar cell by Panasonic. Okay, you can click this link to look into the, I think there are animations and stuff like that, in order to explain layer by layer details of this device. Okay, Panasonic heterojunction solar cell. And then we're going to finish tomorrow, inshallah, on heterojunction. Then we're going to continue with MOSFET on the next lecture. So is it okay so far on semiconductor heterojunction? Can you follow? Okay, any questions so far about heterojunction? All good. Nanti bila kita dah masuk device, when we start talking about devices, solar cells, MOSFET, then you're going to see that you're going to combine all of the previous, or most, if not all, most of the previous underlying principle in the physics of a semiconductor in the real devices. So you're going to see many different new parameters which need to be correlated with the physics of the semiconductor materials that we learned in the last few weeks. Okay. All right, that's all right. So I'll see you tomorrow then, inshallah. Bye-bye. Take care. Assalamualaikum. Stay safe. Where do you get a question for test 2? Where do you get the question? From my brain. Good question, Aziz. It's from my brain, of course. Okay, then I'll see you tomorrow. Bye. Assalamualaikum.